Okay, so welcome everyone to our next event. So I think I can skip now all information. The rest information we keep until the end. So what's going to happen the next 1.5 hours for those who are going to watch the stream? We give a space to our beautiful speaker, where we'll spend some time talking about probabilistic modeling using Pyro library. Then if any questions, you can put them in the chats. If we have time, we're going to answer them. And then I think we're going to conclude our stream, and then it will be some time for us. Yeah, I just want to say to do negotiations, so kind of good.
Yeah. Hi, thanks for turning up, and thanks for joining us today. My name is Giulia. I am working here at Objective Platform as a data scientist in the data science team, and together with the machine learning engineers, with the whole data dev team, we are maintaining probabilistic models for marketing measurement. And in that sense, we want to give you today a small introduction to Pyro, which is one framework for probabilistic programming in Python, but more about that in a second. Exactly. So the goals for today are going to be to understand the basic building blocks of Pyro, to understand how to build like a simple linear regression in Pyro. That's also going to be done in like an interactive coding exercise where we work together to make like a nice model out of some sample data. We're going to also take a break after that, after those first two parts of the workshop, and then we are going to look at one, I think, particularly nice use case also for beginners of Pyro and in this sort of probabilistic programming with those exercises with variational autoencoder. We're first going to have like a quick introduction of what is actually a variational autoencoder versus just a regular autoencoder. And then we're actually going to get our hands dirty and are going to build one with Pyro. This is also going to be mostly collaborative. We are actually going to keep the theory rather high level. We're going to give like an introduction to some of the basic concepts that are just very good to understand when working with Pyro, but we're going to focus on practical coding exercises that we then can also do individually, but of course also with support from like your peers basically, and myself, of course, where you can then also ask any questions that you might have. Before we go further, I have one question to start off. Who here is like already a little bit familiar with PyTorch? A little bit. Okay, not so much. That's okay. So we're going to get into it a little bit more in a minute. But Pyro is built on top of PyTorch, so some PyTorch knowledge is advantageous, but not necessarily necessary. But if you look into the repository that we linked on the meetup page, there is actually a PyTorch cheat sheet where I, just put some basic use cases, some examples of how to work with PyTorch, how to use PyTorch. It's not a comprehensive guide by any means. I just got the idea for that this morning, actually. But I think it can be helpful for people who maybe need a refresher or need to get some guidance with the basic use cases. Okay, with that said, let's get started with part 0 of the workshop. That is setting up the workspace. Of course, that needs to come before we go into any coding. For everybody who hasn't done that so far, I would recommend to. Oh, am I visible here? Actually, that's that's what I do.
Yeah, the thing is, you can remove this. You don't need this because it's not. You can just remove this. It's not going anywhere.
Okay, how do I remove this one?
Good question.
I mean, I think it's just in the corner. It's not so bad, right?
Yeah.
Exactly. So please start your laptops, and yeah, depending on how familiar you are with the question.
Which is the Wi-Fi.
Oh, sorry. Objective Partners guest, and that is sorry. I should have actually led with that. That's actually quite important, isn't it? Yeah, I will give you some minutes to set up that Wi-Fi.
Yeah, sure.
Everybody doing good with Wi-Fi? Objective partners, yes. Yeah, exactly. And then if you have the Wi-Fi all set up, you essentially have two options to get the repo or get the notebooks running. On one side, you can of course do it locally. I think people who are used to that kind of like local work will already know what to do. Otherwise, here's like a
Go there, yeah. Yes.
Okay. I hope I'm
Yeah.
okay visible
Yeah,
from the slide.
yeah.
Okay, great.
We just continue things.
Yeah, if you guys can just let me know once you have everything set up and you're ready to go, and that would be very nice, and we can proceed with the actual workshop. All good? Working well? Nice. I didn't see like any questions from like the stream or anything.
You don't need, because it's on YouTube, so we don't need to go to another. We're gonna pass it to you.
Okay.
So don't worry.
Perfect. Everybody's doing good so far? Like any questions? Doing well? Okay, nice. Because then maybe I can already slowly proceed to the next few points. Or you need some more minutes? It's going okay? Okay, great. Okay, getting started. First actual part, linear regression Pyro. This part, we're going to start it off with a quick introduction to the basic building blocks of Pyro, to give you a rough idea about how models in Pyro work, and we're going to move on to the coding exercise. Exactly. So first off, what is Pyro? I already kind of hinted at it. So Pyro is essentially a framework for probabilistic programming in Python, and it is built on the PyTorch framework, which probably most of you have at least heard, even if you're not very familiar with it. It essentially allows us to extend the basic use case of PyTorch of completely unconstrained parameters, and allows us to introduce constraint into these parameters. Specifically, we can introduce these constraints to prior assumptions on parameters, so prior distributions that we expect our posteriors parameters or results to have. This allows us to influence the outcome of a model, of a complex deep neural network, or also just of a very shallow linear regression with our prior assumptions about the modeling outcome. For us here at OP, this is particularly important because we work directly with non-technical stakeholders to whom we need to explain our models to. And it is very important that the parameters, that the coefficients in our regressions take on sensible values. A very simple example of that, or a very basic example of that, is the non-negativity of media. So we basically try to predict sales, for example, or website traffic in some cases, for our clients with the media that they use, with the reach that they achieve with the media. And it would be quite hard to sell our modeling output if this effect was at some point negative, for example, so that they lose actually traffic or sales when they increase the media reach. So this is, for example, an assumption that we can include in our models through these priors. We're also going to see that in action in a few minutes in our coding notebook. Yes, and of course, through these priors that we can set, these also act as a regularization of our coefficients, so that for example, a linear regression model built with Pyro can still perform well in very high dimensional spaces with sparse data, so with very few observations, which is a very common use case actually in marketing measurement, and a very common use case here at Objective Platform. If you have like any questions about these points at any point, I think feel free to ask. I think we're not under a lot of time pressure. Yes, please.
Is there like a library that works with TensorFlow, or can I use Pyro on TensorFlow? Or...
I'm not an expert on TensorFlow or libraries that interact with TensorFlow, but I think, but maybe someone from the internals here can correct me if I'm wrong. PyMC is built on top of TensorFlow, but I think not in the same way as PyTorch is, because the thing is, if you're familiar with PyTorch, pretty much everything that we're going to look at today is going to seem kind of familiar with a new twist. I don't think the relationship between TensorFlow and PyMC is quite as tightly knit. Thank you. Any other questions for so far? Because otherwise, we would start with the basic building blocks of Pyro models that you are going to need for today, or that would be good to have for today. At the very top, we have the Pyro module. So this is a class, a superclass that we're going to need to subclass PyTorch modules. So that includes our networks and our layers, linear layers, convolution layers. Exactly. Then we're going to have our Pyro samples. These basically specify the prior distribution that we sample our coefficients, for example, from, and our observations from. We will see this in action in a few minutes. And then some more theoretical parts. The Pyro plate is just a technical implementation of plate notation of graphical models. I'm going to also see this in a second, because this is of course not very telling yet. And then the SVI class, I think that's how you say it properly in English, stands for stochastic variational inference, which is the main inference algorithm of Pyro. As I said, we're not going to go too much into the theory behind this. Of course, there's like a lot of theory to explore there, but we're going to keep it high level and practical today. But it's good to know what it is and how it works code-wise, which we are going to see in a few minutes. So first, we have the Pyro module. So Pyro in general is a relatively thin wrapper in most cases around PyTorch. So we are going to be mainly working with like the regular PyTorch modules, but we are going to subclass them as a Pyro module. This allows parameters of PyTorch layers, for example, of the linear layer, weight and bias attributes, to be Pyro samples, which would otherwise not be possible. And it makes sure that the parameters of our, for example, linear layer, our models in general, are actually registered with the Pyro parameter store. Otherwise, it would come to collisions between parameter naming. Again, in here is basically just an example how the parameter store is empty before I initialize and run my linear layer as a Pyro submodule, and how it's then actually filled with the weight and bias. Just as like a simple example. Exactly, here you can see the usage also of Pyro module. Maybe as a quick note, we're going to see this also in part 2, actually, in a bit more detail, that Pyro modules like this, like written as up here, is basically used or is used to initialize new classes. If we want to register existing instances with Pyro, we would use pyro.module as an alternative for this second use case. But we're going to see this in action in a few minutes. Exactly. This is probably the most important building block to understand at this moment. Basically, it allows us to set for the weight and the bias of our actually, I have also made a frame for it. Again, this basically allows us to set a prior distribution for our weight and our bias. Here in this case, we assume the author of this code, which I think was me, but I'm not sure anymore, basically assumes that the weight in the weight attribute of the linear layer is normally distributed with a mean of 0 and a sigma of 1. Here we basically shape this sample so that we can draw batches from the sample, because in most cases we will not have only a single weight parameter here, because we have usually many features in our data. So here we have to specify in this expand statement that actually expands the shape of this distribution, the output features and the input features, and we have to reserve the last 2 dimensions of this distribution as events, because Pyro distinguishes between batch dimensions and event dimensions. Batch dimensions are sampled dimensions. Basically, Pyro assumes that it can add an arbitrary number of batch dimensions to any sample. So we need to actively tell which which dimensions belong to an individual event. Here, this is 2, because we have, I think it's not visible in cell, but I think this is because it's 2 output features and 2 input features and 1 output features. So that makes 2 dimensions that need to be reserved for events. We're going to see this also in action a bit in a few minutes. And then we essentially do the same for the bias parameter, so the intercept in a simple linear model, that we assume that the intercept is normally distributed as with mean 0 and sigma 10. So greater sigma. Here we only need to specify the number of output features, which in this case is 1, because we only have 1 intercept per model, and then we have to reserve only 1 dimension as an event. I think that is that for the Pyro sample. Exactly here, similar to the Pyro dot module syntax. If you want to restrict or put a sample as an attribute of a PyTorch or of a Pyro module, basically, then you can use Pyro sample like in this example. For other variables, you can use Pyro dot sample. Any questions so far? Not yet. I think the event syntax is also going to become a bit clearer in the coding exercise that we're going to do in a bit. Pyro plate and the next step are a bit smaller in terms of amount of things that you can understand there. So basically, this Pyro plate syntax that you also see here at the bottom is technical implementation of the plate notation that you see in this graphical model here. This is just an arbitrary example where we have different coefficients, A, B, A, B, R, B, A, R, and sigma. We don't need to worry too much about what these are for now. So just arbitrary samples, arbitrary coefficients from a hypothetical model. And then we have here our our observations, but A, B, A, B, R, if these are coefficients of a linear model, these are sampled only once. We only have 1 value for them across the entire model, but ops is not only 1 value, this is many value observations. We have usually many observations in a model. And plate notation is a way of expressing that this is sampled n times or multiple times, specifically for the number of observations that we have. And it is implemented like this. We use a context manager with pyro.plate. Then we give a name to our plate. This is just something that Pyro needs for its internal parameter store. We don't need to worry too much about this, just that the name is actually unique. And then we need to supply the n. So how many times do we actually want to sample here? We have x as our input data. So we want to sample as many times as we have observations in x, basically for each row in x. We want to sample from observations 1 time, specifically distributed with the mean that comes from our linear layer. That's the output of our, the deterministic output of our model, and with a sigma that is defined here with our Pyro sample statement that we have seen on the previous slide. Exactly. So this is the basis of the Pyro plate statement. This is also something that we're going to need in a few minutes. Exactly. And then the SVI or SVI class, as I said, stands for stochastic variation inference, and is for how Pyro learns, essentially. So it's the main learning algorithm for Pyro. There are some other learning mechanisms that are supported by Pyro, but we're not going to go too much into detail for those today. And here you can see on the right side an example of how you would implement this. So an SVI class needs a model, an arbitrary Pyro model that you defined earlier. It needs a guide. You don't need to worry too much right now what the guide is, but it is essentially an approximation or a mechanism to approximate the posterior distributions of coefficients in the case of a linear regression. Pyro is very, very flexible in terms of what kind of guides you can define for inference. We are also going to define our own guide in part 2 of this workshop, but in part 1, we're going to look at a very simple linear regression model. For these kind of simple, straightforward use cases, Pyro provides a good amount of auto guides, or guides that you don't necessarily need to define yourself. So there's the example that you see here that we initialize by passing our model. Then we need Adam, our optimizer. People that are familiar with deep learning are probably kind of familiar with it already. Notice that the way we pass arguments to the Pyro Adam is just slightly different than it is with TensorFlow and PyTorch. And then we have to define our loss. We cannot really use a loss here that, like most people are used to, like mean squared error or something like that. We, in our case, are going to use the elbow loss, and the trace elbow is like the negative elbow. The elbow itself, this number is a lower bound on the evidence that we see in the model. Basically, it tells us how, in simple terms, it tells us how good our model is, and the negative value of that is what we can use as our loss function to optimize. And at the bottom, you see a very simple training loop for Pyro using the SVE class. And its step method, passing our data to the step method, will perform a step in the parameter space and return our loss that we can accumulate, display however we want later on. So this is it for the basic building blocks of Pyro. Any questions so far? Because otherwise, we would move on to the next section. Nice. Okay, time to get coding. So if you have set up your local workspace, you can find a folder workshop, and then part 1, linear modeling with Pyro, empty template.ipynv. This contains the, let's say, the skeleton of a linear Bayesian regression model. That, the coding exercise would be to fill that skeleton with life. If you're using Google Colab, then you should see it in your browser. And I would give you all a few minutes to take a look at the notebook. Maybe get started with the exercise. Try and cross off the to-dos. And then if any questions, of course, feel free to ask. And otherwise, then in a few minutes, we can also take a look together. I assume everybody was able to find the notebook and open it, and I hope also run it. I also recommend to maybe keep the slides open if you can next to it, so you can maybe take a look at the examples from the previous slide a little bit. I think that can be helpful to define like the Pyro sample, define the Pyro plate. If you have any specific question already, feel also free to ask.
Okay.
Yes.
Can I ask you about the case? Because you predict sales, is that the number of sales? Because it's the numbers you target?
Oh, excellent question. The original file was actually called sales.csv. I transformed it to be revenue. So technically the name is misleading, but I didn't think of actually renaming the file. Thank you for raising that.
So your
The
input-
variable, huh? Or
Sorry?
the variable is also sales.
Yeah,
Yeah,
and
exactly.
Variable sales indeed. So your inputs are your media channels and your output is your revenue.
Yes, exactly. I thought of calling the model revenue model, I think, but I did not think
Yeah, the
of.
model is called revenue. That's correct. So and it's not really related to Pyro, but I like to imagine what I'm doing. The media channels is also numbers.
Yes, of course, feel free also to take a look at the data frame. It's essentially the amount of money spent on different media channels. Like I think we have affiliate in there, Facebook.
Yeah,
some
so it's a
other things.
budget.
Yeah, exactly. So how much money did the client, this hypothetical client, this is not a real data set, of course, how much did they spend on Facebook and TV and other channels? And how much revenue did they make with sales of the two models? With that in mind, we can also maybe think about what kind of value would make sense. Because if we now ask the question, okay, how much revenue did they make per unit money spent on these kind of channels? What would be a reasonable value? Like what would be something that I could go to the marketeer and tell him, hey, this is the case. If it's -10, probably not, right? So we need to find like some kind of reasonable value, set that as the prior with the Pyro sample, and then let the model learn to find a compromise between the prior and the posterior. You can have the same consideration for the intercept. What would be a reasonable baseline? If we would not spend any money on any media, how many sales would we make? How certain are we about that? What kind of prior assumptions? That's essentially what priors are about. What kind of prior assumptions can we make? I would, of course, not worry too much about this necessarily. It's more like to give you an idea about the process. We're not going to have like a competition. Can do the best model. If you want to do that, maybe you can do it.
One comments.
Yeah,
From my colleague.
Oh, thank you. I actually don't speak Italian, despite my name.
That's how it's usually confusing.
But I get that a lot.
But it's still syntax learning.
Indeed. Maybe after I'm done with Pyro, maybe I will pick up Italian. Although I'm living here for 3 years now, I maybe should pick up Dutch first.
Speak with Jacopo.
Yeah, I can train with him. Do we have any other Italians in the company? I don't think so. Of course.
And Gabriel?
Sorry.
Yeah.
She's also Italian. You know. Okay, nice.
GDPR information. Who goes online? Beware.
Oh, yeah, of course. You don't want to dox anybody. Maybe give like I don't really have a clock to hand, but like 5 more minutes, and then we go through it together. Does it make sense? Yeah. And as I said, like if you have any particular questions about how something works, feel free to ask. If you need like some tips for PyTorch specifically, feel free to take a look at the cheat sheet, which you can also find in the repository.
What's the name of the cheat sheet?
Just be PyTorch cheat sheet. Just on I think in the workshop folder. Maybe on the solutions folder. Yeah,
Maybe the brand or something.
maybe. Just gonna take a look. Now, yes, PyTorch cheat sheet. There we go, in the workshop folder.
Just need to dig for.
Yeah, exactly. If you have it locally, you would need to do a quick git pull. Okay, thanks for pointing it out to me.
You mentioned that just without my.
Yeah. Of course, if either right now or in the future you're curious about like an example solution, there's also solutions folder in the same repo that you can find for both parts, for this part and for the next part. Yeah, an example solution. As in many machine learning use cases, there's not a single perfect solution, but there are different solutions. You know, especially in the second part, experimentation could really still pay off to improve the performance of the model. So, of course, feel free to also try things.
It's very well documented. Thank you.
Thank you for that.
Really helps us, especially for the workshop.
Appreciate that. I would say we are about ready to maybe walk through it together. Like that's okay. Maybe you just need some inspiration.
It's complete to me. Don't say anything else to me.
Yeah. Yeah. If people are as far as having already like even everything completed, I'm not sure if I should walk through like every single line of code because or like, can I get like an idea about, was it very, very difficult, or was it quite doable, or very easy, maybe even to follow through? I just want to gauge how much into detail I should go with the explanations, also in the interest of time. If I just now say stuff that you already, if that is clear to you, then it's not very efficient.
I looked at the data a little bit because I was curious. So you have like sales of 2 products, and the media is a number of channels, and then with date.
Yeah,
some
exactly.
customer of yours spend per day per channel some
I think
amount
it's
and-
weekly aggregated data. So it should be at least, so the date should be like Mondays of weeks. And yes, indeed. So in the week of that Monday, the hypothetical client, as I said, it's of course not actual client data, spend like a certain amount of money on, I don't know, like TV, for example, and made also a certain amount of revenue through product A and product B. And now what our goal basically is to explain how much return on ad spend, we would say, the client gets from his media investment. Exactly. And there's of course a use case where we can have like some prior assumptions, also even as like non-marketeers, just think about it a little bit. Yeah, just to see Pyro in action, basically.
Giulia?
Yes.
We need to zoom a little bit.
Zoom, yeah. Did it zoom now? Is it better? No, I think I cannot. It's like 150%. It's like
Okay.
no, that's
yeah.
oh no, here, there we go.
That's good. Thanks a lot. Thanks.
Okay.
Beautiful.
Okay. Yeah, I think I will switch off to the example solution. And then, you know, if like stuff is like very, very unclear, like obviously just raise your hand. Otherwise, I will just walk through what we're doing. Okay, yeah, I think the first two cells are probably not very interesting, importing stuff and installing the requirements. Then this is the first kind of cell where we need to get active, if I can scroll it properly. Yeah, exactly. So as you have seen, we load the media and the sales data from disk. Parquet files in this particular instance, but it's not very meaningful. Then the first thing that we probably want to do is define our X and Y as torch tensors, because Pyro requires torch tensors to work with, not NumPy arrays. That's maybe the first thing that we that could trip up somebody who is maybe not familiar with Pyro, with PyTorch, I mean. But then we can already get going by defining a model. So I think the signature of the initialization function is, I think, that the same also in the empty template notebook. But essentially what we're doing here is we are defining our class, the revenue model, as a subclass or as inheriting from the Pyro module, because we of course want this model to be a probabilistic one, not a frequentist one. So we don't want to have an ended module, as people familiar with PyTorch might know it. Then we just set some like the number of media channels, the number of sales products. This is not very meaningful right now. This is just our example data that we're basically working with. We need to super init to register all the parameters that we're about to create with the Pyro parameter store to set up some Pyro specific initialization methods. And then we can essentially get into defining our one layer. Obviously, it's just a linear Bayesian regression. So that's like a single linear layer that we want to have. Obviously, if we make a deeper model, we can add more layers. We're also going to do that a little bit later. But for now, we just want to have our one linear layer. We initialize this linear layer as a subclass of Pyro module, and we define just the same as we would do with any linear layer, which you can also see in the PyTorch cheat sheet. The in features and the out features. Out features are a bit cut off now because we zoomed in, but that the in features are obviously the media channels, so the number of input features, 7 in this case, and the out features is the amount of products that we have. In our example, we had 2. Exactly. Now, as you may know, this linear layer is now going to have a weight in the bias. Exactly. The weight is effectively the coefficients in the context of a linear regression, the betas, maybe you know this as betas. Is that clear what this weight is? Yeah, okay, great.
Do you set that? Because that was trained, right?
Exactly, that is trained. And if I would not do anything here, like if I would not do anything Pyro sample, then this would just be a completely free parameter, as it is in a regular PyTorch model, and this would be able to take on any value. In this case, where we have like 7 features and 2 output features, it's maybe not so bad. But as I've mentioned earlier, one of our very common use cases is that we have like very high dimensional data that is also very sparse, so it has very few observations. And if you then have like a completely unconstrained model, and this parameter can just become whatever it wants, there will be some nonsense in there. Values that are not remotely reasonable, and then we cannot, of course, explain that to our non-technical stakeholders, or yeah, it's also just wrong, obviously. So what we're doing here is actually we're using Pyro sample. For now, we can just look at the normal here, at the normal distribution. We're using our Pyro sample as a constraint, basically, around our coefficients. So this is the prior, basically, that we are setting here. Indeed, we are setting here our Pyro sample, we are setting the distribution that we want to sample from, but it is exactly that. It is just the distribution that we are sampling from at the start. These distributions, like the weight distribution, so to speak, will shift over the course of the training as the Pyro under the hood through SVI finds let's say, a compromise, so to speak, between the prior that we set here and the evidence in the data, the posterior, right? And we're going to be able to see this a little bit later. For now, we see here that we set our weights as normally distributed around 1 times 0.5. It's a very basic intuition. We say that every dollar that we spend or every euro that we spend on a media channel, so it should get us one revenue, basically €1 in revenue. And since we have two models, every euro spent should give us, to be, like to be in equilibrium, so to speak, should give us 50 cents back to be efficient. There can be, of course, a lot more thought going to this, like the trade-off between different channels. Some channels are stronger than other ones, or can be expected to be stronger than other ones. But for this basic example, I think this will suffice. That we say, okay, we expect the mu, basically the mean of our prior distribution is 0.5 for each ones times 0.5. Exactly. I'm going to go in the shade in a second, because on the other side, or a little bit further to the right, we see the second parameter. And as you probably know, for a normal distribution is usually parameterized by its mu, which we just said was 0.5 for each channel, and by its standard deviation, sigma, which in this case is set to 1. Why is it set to 1? Essentially, the standard deviation gives the model information, or expresses our prior belief, or how strong do we believe into our prior belief. So, for example, if I would set this sigma very, very high, the standard deviation of my normal distribution prior is very, very high, then I don't have a lot of belief. Then any kind of evidence that the model might find might move this prior in one direction or the other very fast. This is not ideal, of course, because we specifically want to not move too far away from this prior mu to retain like some kind of explainability, some kind of reasonability, basically, in the models or in our results. On the other hand, if we would make this too small, then our model would not have any space to trade off between the prior and the evidence that it finds in the data. So then we wouldn't learn anything from the data, and then we could just also just go with our prior. So this is example trade-off. What kind of parameters to set here? That's probably one of the biggest challenges for all kinds of Bayesian modeling.
And why would it then not learn? Because of the prior, so it can also go away from it, right? Or
It can, to the extent of the sigma. So the prior sigma that we have here is essentially the strength of the regularization. If you're also maybe a bit familiar with ridge regression, a Bayesian regression is actually equivalent to a ridge regression where the coefficients are centered around 0 with a parameter alpha that controls the regularization of the parameters being equivalent, not directly equivalent, but doing the same thing as the sigma here. And it works by the same mechanism. If you would use a ridge regression with a very, very strong penalization, all the coefficients would shrink to 0. You wouldn't essentially learn anything. And it does the same here, except that the coefficients are not centered around 0. They are centered, in this case, around 0.5.
Yeah.
So all the coefficients would shrink towards 0.5. Potentially the result would be absolute nonsense. But that is what that is what would happen if we would set this very, very small. You can think of this as a parameter to regularize the strength of
Yeah,
the
so it
regularization.
doesn't have to stay the mean, but within the distribution, it can only find its mean.
Exactly. So yeah, exactly. Great. Then the next thing is here the bias. It's hang on, before we actually move on to the bias, I want to also talk quickly about the shape of the distribution and also about the fact that we use here a folded distribution. You don't need to worry too much about this. This essentially just tells this distribution that it needs to stay above 0. That's pretty much all, because we don't want to have media coefficients that are negative. Then the shape, if we go over here, we first use we don't use expand actually, because our parameters are already of the batch shape that we want to sample from. So basically, if you look at the linear weights when it is initialized, you will see that we have sales products number of rows basically, and we have media channels number of columns. So it's a sales products X media channels matrix. And we want to basically override this matrix with a Pyro sample distribution of the same shape. And now, as I've just said, it's this is 2-dimensional. So we have 1 dimension for the 2 products, and then 1 dimension for the 7 sales channels. So we need to declare these 2 dimensions that we have as event dimensions, because every single time we draw an event from this distribution, it needs to have 2 dimensions that are reserved for the event itself and not for samples. This is quite important to do, because otherwise there can be some very weird results down the line. Now, here and or any questions so far before we move on to the bias? No. Okay. Here, the bias is the second attribute of the linear layer, and is essentially, in this case, for our linear regression, the intercept. We again define our prior belief about this bias or the intercept. You can see it up there, how we did it basically, or what we defined. We defined a lower bound, and then on the right side, as you can see, an upper bound. Exactly, as torch tensors. And with, if we look at the top, just between 0 times 2 because we have 2 products, and 10,000 times 2 because we have 2 products. And exactly, since this time we only have 1 event dimension, because every time we draw a sample from every time we draw a sample from this distribution, it should have exactly one dimension. Like it should be 1 vector of 2 elements with 1 dimension. So in the end, we say 2 event 1 2 to reserve this 1 dimension. You're thinking from the right for drawing events, for drawing samples from the distribution. Okay. Who made it through the initialization method? Nice. Any other questions before we proceed to the forward method? No, not so far. Okay. At the bottom here, we just assign sales products and so on for later usage. Exactly. Then we have the forward method. If you're a bit familiar with deep learning, you probably are familiar with the forward method. This is basically telling now our model how to use the layers, and later on also the activation function that we just defined, and how to apply them to input. For that, we need the X, our training data, and the Y, our labels, which should be optional. So it can also be none, for a reason that will become clear in a second. So the first thing we want to do is get our Y hat by applying or by passing our X, our training data, through the linear layer. This will get us the mean of our prediction, the average prediction that we expect. like an appropriate vector. So this should be 140 rows. I think we have 140 rows in the data, and 2 columns. And then we define a noise parameter, because as you are aware, most models are not exact. There is always some noise to our data. In a probabilistic model, we need to define it. In this case, we use just a half normal distribution, because noise is always like in this case, it's a positive value, and we just need to use a sigma for parameters of this half normal distribution. We need to expand here as well, because we have one row, so we sample one time, in this case, for 2 different products. So we set the expand shape to 1, comma 2, and we sample only, or we reserve only one of those dimensions, here the second dimension, as an event dimension, because every single individual sample that we draw should have, like this, basically the second dimension describes the event. Now that we have defined our noise as well, we go further down to the Pyro plate statement. Now this is like a little bit special. We need to have here 2 Pyro plate statements, because we need to sample one time for the 2 products that we have, and one time for the 140 rows that we have in the input data. If our input data would be batch, and we would have batches of 10 or something, that would be fine, then this would be a 10. Accordingly, this is just the length of the input. I think this is pretty straightforward. We just need to define a nested plate where the innermost dimension, the samples, basically, I just call it samples here. So the 2 products comes first. Also using here self-sales products as the number of samples to draw in the plate, and where the leftmost dimension, so the 140 samples to draw for the size of the training data, comes second. Exactly. Like it's also like written out, I think, I hope quite clearly in between the plate statements. Yes, and then we need to sample now from our observations as a normal distribution, as is common. You could also use a uniform distribution. This is not too uncommon. With our y hat, which should already be in the shape of 140 rows and 2 products, and the noise, which has only 1 row but 2 products, but because we are in a plate, so we sample 140 times here, it knows to sample this independently 140 times. And then, and this is not the important, the very training relevant part in this forward pass, is that we need to pass our observations y to the Pyro sample function to basically tell Pyro that these are the actual observations that we made. This is what enables Pyro to learn. Now, why is it optional? That is because, of course, if you want to make a prediction about the future, and we have X but no labels for it, then we want to not pass this, but still be able to get the expected value, for example. We could also make a more complicated inference about the y hat to get like the full distribution of the prediction. But we're not going to do that for now. We're going to focus at looking at the distribution of the individual coefficients later on. Okay. Somebody made it all the way through the forward pass as well?
Julia, a quick question.
Yeah.
In the slides that you showed, there was for the linear sample for the y hat, there was also squeeze.
Yeah.
What did it do?
Good question. So if I scroll up here, exactly. So you have in one of the example slides, we say here set the linear layer x dot squeeze -1. This is because a linear layer, I think it's the same for Pyro and PyTorch. It's not Pyro specific. It will return always 2 dimensions. So it will return 1 batch dimension essentially, which will be 140 of length 140 in this case, and it will return 1 more dimension that just contains the value itself. So the output of this would be, in the case of us having just 1 product, would be 140,1. That would be the shape of y hat here. So it would be 2-dimensional. But if our actual input is only 1 dimension, this can lead to some funky behavior with the loss function. So if we have only 1 product, for example, or only one dependent variable, it can be beneficial to add squeeze -1 here to make sure it's really just a 1D vector, the same as our input variable. In this case, our output has naturally 2 dimensions because we also have 2 dependent variables, say for product A and say for product B. So we don't need to squeeze anything here. Thank you. Yes.
I don't think I fully understand the plate, because what do you mean if you say we are in a plate?
This essentially just tells Pyro that something needs to be sampled multiple times.
Okay.
This is pretty much all. If you would just have one product, like just product A, then you would only need to have this. To basically exactly to basically tell Pyro that okay, we have our linear weight and our linear bias, like further top, and these are just there is just one of them. Like these are not different for all of the samples that we're looking at. There's just one sample, but the noise and the observation itself, that's going to be different for each sample, of course. So we need to tell Pyro, or actually we can tell Pyro. There are also other ways of doing this, but I think this is the most efficient computationally, and I think also the clearest one. We need to tell Pyro that this is going to be sampled many times individually. So we are not just drawing one big batch, but we are drawing len X samples individually.
Okay.
Does that help?
Yeah.
Okay, great.
Why do you do the 2 products at the same time?
Yeah, honestly, it was kind of a design decision, so to speak, on my side to show you how Pyro works with 2 dependent variables at the same time. Yeah, that was
We could sample, for instance, sigmas that are related, right? So if 2 products would be related, that would allow us to
actually have a 2 stage.
Exactly. So it would be possible with Pyro to define that the priors of the 2 individual models should be drawn from the same distribution. So that means they can learn individually, but be dependent on the same prior. Same for the noise as well. But for the sake of this being like a not advanced workshop, we're going to skip that one for now.
That's more a thing that you could that we could investigate.
Exactly, indeed. Any other questions before we move on? Because I think the next part is then already the training. We're almost done. Nothing for now. Okay. I hear this. It's just, this is a way to graphically visualize basically the model that you've just built. As it puts in the comment, you need some system dependency. So I'm not sure if everybody was able to do that. But here we basically just see that observations is twice plated. Sample has 2 samples basically, and data has 140 samples, and then observations then depend on linear layer weight, linear layer bias, and noise, which are all outside, defined outside of the plates. It's just a nice way to visualize your model. I don't think you need to worry too much about it. This is an investigation to see this can help with debugging. It's a way to see the tensor shapes with event dimensions and batch dimensions to the left of the pipe at each parameter side. Also, this mainly for debugging. Wouldn't worry too much about it for now. Exactly. The guide, as I've put it in the notebook as well, we could define our own guide here. As I said, Pyro guides are arbitrarily flexible when it comes to how the inference is to be done. For the purpose of this, we are also going to define a guide a bit later in part 2. But for now, we're just going with one of the auto guides that Pyro provides. And then we are already at the training loop. Exactly. We define our model. We define our guide as being dependent on our model. We define our optimizer with a suitable learning rate. Now, we can, of course, also experiment here. We define our loss function and then our SVI class with passing all these parameters that we just defined. And then we can get into our loop. The number of training loops is chosen arbitrarily. Of course, with purely frequent risk models, you should stop at some point because otherwise they will come to overfitting. With these kinds of probabilistic models, so they are fairly resistant towards overfitting. We're also going to see an example of that later. But yeah, you could set it to more. You could maybe set it to less. Just it needs to be sufficient to learn the posteriors. And inside the training loop, we can really just call stri.step xy, basically the same way as I showed it in the example earlier. And yeah, just do that about 1,000 times or however many it was. And here we can see how our negative elbow actually decreases to a sufficiently low value. Based on this, maybe we could even do some more epochs, but that's not too relevant right now. Exactly. And here, this is now how we do inference. So this is now that we have our model, like we need to see what are the results, what are the distributions over our coefficients and potentially over other parameters that we're interested in. And we do this by defining this predictive class from Pyro info predictive. It needs the model that we have just trained and the guide with which it was trained. It needs to draw a number of samples for each parameter. The more samples you draw, the longer it will take to actually draw them, but the more accurate, so to speak, the posterior distributions will be. Exactly, and this is where you actually draw the samples by passing your X. This could be now new data, unseen data, testing data. In this case, it's just the training data again, just to see what we learned, what the model learned. Exactly, and then we can access the linear layout of weight. So these are the coefficients of our linear regression model from this dictionary. Note that we will have 10,000 samples in this tensor. So we need to reshape it to and potentially arbitrarily added dimensions, which predictive can do, which is a bit unintuitive. But we need to reshape it like this to make sure that it has the expected shape for our 2 products and 7 media channels. We need to convert it to a NumPy array, and exactly in this exactly. And here we need to here I just shifted an axis to move an axis out of the way. I don't think this is very relevant. But then we can take the actual mean across, or take this visualize the actual distribution across the linear layer.weight, so across the different parameters that we have. There's now a little bit scrunched together because I had zoomed in earlier. Yeah, it's not very well visible, but now we can basically compare the distributions of coefficients across the different media channels and across the 2 products. So first thing that we can observe is that they are all in a relatively reasonable range across the prior mean. So they're all around 0.5, which is good, which is what we wanted to achieve. And then we can see that some of them are higher. This, I think this is oh, sorry. Here, this is display. So display is a winner in our case because the number is higher. That means we make more money for each euro we spend. While other parameters or other coefficients are a bit lower. So I think this is TV third one here. Yeah, exactly, which is it's making only on average about 0.35 euros for every euro spent. So it's maybe a loser channel to not invest in if we want to maximize our revenue. But these are the estimated posteriors of our coefficients. Any questions so far for this on this part? Is it clear how we got to this point? Like what is underlying this, like these distributions? Maybe not. Maybe it is, but it's fine. I would say we are already at it for an hour. Next part would be the break part, where you can grab some snacks, network, get a drink, maybe ask me some questions, and just relax for a bit. Sounds good.
Yeah.
Thank you. Exactly. I was thinking 15 minutes or something like that. Yeah.
It's too much. Yeah. This I can change my shape. This one. So we'll work with I think 5 minute break, right?
Yeah.
I was thinking
50?
but
Yeah, is it not?
when did we say the second level representation should begin? How much should we apply?
Yeah. Let's say 5 first, yeah?
Okay, okay.
Will
Then,
5 minutes work for you? 5 minute break? Yeah. Because otherwise we don't have time to.
But I would like to ask, so click on this for a second. And that.
here, no, you?
Yeah, the second one, that's the, and just put it. Okay, if you put like this.
I just want to pick my
Just one moment to set some data.
Ja, wel gewoon, daarom de dingen, eigenlijk het werk gewoon via Google Drive. Het is wel handig.
Okay. No, just and if you put like this, what's gonna happen? If you put like this, because it has at least like at least 1 minute delay.
Okay.
Let's check. No, it's not picking up. Okay, so just put to this, don't worry. Yeah.
Okay.
So let's have some.
Are you working?
Yeah.
Want to drink something or? I forget my passport for my school, so I can't go as an administrator from the terminal. I try to,
remember all the passwords. And now, yeah, now it's running. Oh yeah, okay. Yeah, but this took me for actually quite long. And now it's running. Maybe you can catch up. Now I need to write it down somewhere. Oh.
And yeah, also like more visual. Yeah, and more like picture.
I think we talk about development. Yeah, cool.
I'm always like, I put the skin pants. No, I don't know Pyro. Yeah, I know Pyro, but I don't know. Years ago, so I really need a refreshing. Well, I'm working there. Okay, so it was rather that it was really no, here. You start with the layers. Then layers and then leads and buyers. Because if you want to do one to buy. This is cool. This is what are like the variation. But there is like a series of there is like a series of yeah, and then there was This one. Something like yeah, I see how that. Yeah, I don't crack my. Yeah. Also, and we have the work. Very like. Yeah.
Okay. Well, you put some pictures, I don't. You're going to put on the meetup page, I guess. Yes.
Yes, just. Back, you can also like feel free to share this in ways with what they're on. The rest, like the program is everyone's wants to get on. Yeah. But there's a big system. I'm sure all they. Yeah. Yeah.
It's Because I would, love to join as well as like your personal review things. In fact, it's not like the person, not the virtual words.
Yeah, we're actually, you guys have already like it's one of us. So we can go there and see. It's a little more. Maybe we'll get us for the next one. Yeah. This is not. We try it as well. We want to also like in a year. Yeah. Okay, I think we can start already. Yeah. Yes, yeah. Wonderful folks. We get in Dashmote, grab your voices. What with foods? Let's continue and then we can more time. More things. I will take one.
Do we get like any questions on like YouTube or anything?
Not right now.
Maybe
But there are the Italians.
Welcome here. That's a workshop session.
Are we all set from the streaming side?
Yeah, it was
Okay,
still
okay.
streaming, which is then cut it out.
Yeah. Okay. Welcome back, everybody.
Yeah.
Yeah, no worries. No
Yeah.
worries. Yeah. Welcome back, everybody. We have a second part, exactly, in which we're going to talk about variational autoencoders. Variational autoencoders are like, I think, a fun way to explore the capabilities of Pyro, to see what Pyro can do, and to see like one of the specific use cases of this kind of probabilistic deep neural networks. First, we're going to start with having a quick introduction of what autoencoders are quickly, then what the difference to that is a variational autoencoder, and then we're going to get into the coding practice with another notebook. If at any point you have like questions about this part, or do you have any questions about the previous part, feel free to ask. Otherwise, afterwards, there's still going to be some time for that. Okay. First, let's get started with autoencoders. So the idea of autoencoders is that we have some input X, and through an encoder neural network of arbitrary shape, arbitrary layers, we compress this input into fewer dimensions. And this is basically then the latent space. And then we have a second network, that's a decoder, which is most commonly symmetrical to the encoder, that decompresses the latent layer, so the compressed layer in the middle, back into ideally the original shape. There will usually be some kind of loss here, so this will not be exactly the same as this, except if our encoder and decoder are perfect, but that's usually not the case. But the idea here is that we find basically that latent representation, that low dimensional representation of our input features that retain the most amount of information that can then, of course, be reconstructed through the decoder back into the original data. The usage of this is usually something like compression, as I mentioned already, or also just dimensionality reduction. So basically a more sophisticated, you want to say maybe PCA, for example. So we start with many input dimensions, 100, and we end with less input dimensions, 2 that can then be used, for example, by a model. Now, one maybe shortcoming, so to speak, of an autoencoder like this is that this latent space is completely unregularized. So what exactly happens here, how the features are going to look, it's not meaningful. They are not constrained to anything. They can fit in any way, basically. And we see this actually if we go on the next slide, where we have some examples. We are, by the way, going to work with the MNIST digits data set later on. So here are some examples from that. So here is the original digit as an input sample, basically. Here is the reconstructed digit. So after we pass it through the encoder into the latent space and then through the decoder to the reconstructed input feature, it looks like this. Maybe it's a little bit blurrier. Not sure if you can see it on this big screen, but it's pretty good. Like it's like based just on a simple autoencoder, we are able to reconstruct the original feature pretty well. However, if now we draw samples from the latent space, so we just try and draw samples from the space that is defined by the latent features, we end up with nothing essentially. But the top one and the bottom one, they are nothing. The middle one, maybe you could guess that that could be a 3 with a little bit of fantasy, but it's not a meaningful sample. Exactly. And now, opposed to this unrestricted latent space, we have variational encoders, which are conceptually quite similar in the sense that you have an input, an encoder model, a latent space, a decoder, and then hopefully the same output. But as opposed to the regular autoencoder, a variational autoencoder does on one side, every time we do a decoding here from this encoded sample, we will get a slightly different result because this is not a deterministic thing. This is not a deterministic point in the latent space, number one. And number two, this space is actually meaningful. Here we have like a constrained area of latent features that we can sample from and actually get some kind of meaningful sample that then looks in a way like the input, but is not the input. So we have actually generated a new sample. The variational autoencoder that we're going to look at today is a rather simple architecture. There are like many extensions to this. But if we go on the next slide, actually let me go to this one first. We can see some examples that were generated with this variational autoencoder. Not all of them are going to be very nice. So here we can see this is maybe halfway between a 3 and a 5 or something. But maybe that's a bit meaningful. This, I think we can clearly see that it's a 5. This we can see that it's pretty clearly probably a 9. Could technically also be a 7, but I think that's a pretty clear 9. Here in the middle, we see also some reconstructed digits from this original digit input. Not sure how. Yeah, I think it should be quite visible, right? That this is not the same. They are very similar, of course, but they are not the same. So every time, as I said, if we reconstruct or if we pass basically a digit through this variational autoencoder, we will get a slightly different output. And now one slide back, exactly here, just for visualizing how this could look in 2 dimensions, the underlying variational autoencoder that produced these samples had, I think, 32 latent dimensions. But if we actually project these 32 dimensions into 2 dimensions to be able to visualize it like that, like as a scatter plot, we can see that there are very distinct clusters. These clusters, as you can see here, describe or consist of the digits basically that make up our MNIST digits data set. And you can see that, for example, here this is, for example, 7. This is 1. So we would, of course, expect all the 7s to be together and all the 1s to be together, but 7 and 1 are two quite similar digits. So we would expect these also to be together. And in fact, we would expect that if we sample from this region, we get a 7, a meaningful 7. If we sample from this region, we get a meaningful 1. And if we sample, anywhere in between these two clusters, we get something that transforms from a 1 to a 7 or from a 7 to a 1 until we actually reach a cluster and it becomes a 1 or a 7. So essentially, the latent space that we're looking at, we would expect every sample that we draw from it to be meaningful in some way, not be noise as we have seen from the autoencoder. Exactly. This is just as like an additional example lifted from the documentation of Pyro, where the author of the documentation built a simple variational autoencoder with Pyro that and basically just drew samples from it. As you can see, there are quite some numbers that look quite correct. Not all of these look quite correct, either because the model is not good enough or because they were drawn from an awkward space in the sample space. This is about the quality that we can expect from our model. The model specifically in the solution is a little bit more advanced, so it can draw a little bit better samples, I think. But if we want to become better, basically, we can think about doing some experimentation with the layers that we're using in the models that we're about to explore, or we can think about, and that would be maybe then something for a deep dive, on expanding on the concept of variational autoencoders, because there are several newer concepts, newer models beyond that would be able to draw better samples, but that's maybe for a different session. Any questions so far? Not so far. Question? Okay. Because then, another coding exercise, variational autoencoder, part 2. Again, I will give you like some minutes to explore the notebook, take a look, maybe take a shot at it, ask any specific questions that you would like, and then we can take a look together. maybe 5 more minutes. And we can go through it together. Or if there are any questions until then, of course, you can also ask. Hope you find the comments useful. Yeah, the idea is also because it's probably going to be quite difficult to now understand everything and be able to do everything that we talked about now, just like this. So the idea is also going to be, and that's also the invitation to all of you, to take a look at these notebooks also afterwards, because they can also be enjoyed, I hope, independently of this, basically. Yeah, and then to also like experiment with it a little bit, like experiment with setting different priors, for example, for the Bayesian regression that we did in part 1, by using different kinds of networks for the variational autoencoder, for example, or all sorts of things, basically. Of course, you can reach out to me on Meetup if you have any questions. Otherwise, Google also helps, of course, although the community for Pyro is not that big. So sometimes it can be difficult to find, if you have specific questions about Pyro, sometimes it can be difficult to find answers to just Googling. But yeah, as I said, like I am reachable.
Have at least one colleague who contributes currently to non-Pyro library.
NumPy?
Non-Pyro library.
Ah, okay. What do you? Later. Okay, let's have a conversation later. Of course, yeah, everything's recorded now.
I also want to add that, like, if you never done any Bayesian before, it could be really hard in the beginning. You just need to get used to it.
Yeah.
And just time.
Yeah, of course. Like this is also why we're really going light on like the theoretical concepts. Where we're staying very high level. The goal is just really to show you like some of the things that Pyro can do. Maybe get your hands a little bit dirty, and then if you like it, take it from there. Two more minutes. Yes.
If I try to run the solution, I get an error. I don't understand.
What is the error?
It gets a lot of names. It's a very hard answer.
Yeah. Can you try to run it again?
Just the whole notebook?
Just the cell above that. Like from there.
I split it up just to understand it.
Yeah.
No, it's outside the mix. I can let you know when it's finished.
I mean, if it goes, no, indeed, like so, running this will take quite some time, like the solution. So if you want to make this your own quick network. It can happen that during initialization sometimes something that weird happens. I'm also not exactly sure why that happens actually, but somehow the gradients die. But in those cases, you can just run it again. Here, the law as
yeah, it's just here, yeah.
Exactly here, and just a little bit
Okay. So what are these sentences? That says we can input between one of the sentences. What changes this is maybe. And then in the middle, that's it. One yes. Encoded. What is this process actually? Mapping.
Can I,
Yeah.
latent space and decoder and right?
Yeah.
I don't understand this process. Not actually the input to a one latent space. What's actually happening for this mapping process?
Now mapping is maybe not the right word, but this is essentially just like the forward pass. I think we're in the encoded here. Right? Yeah, exactly. So basically, this is just the process of applying the layers that you have defined up here to the X, and then if maybe we should say
The X is all the images
compressing or exactly it is indeed compressing, and we need this may be a bit not very clearly expressed by me, but we need in the end to have this like what, so this latent space. Basically this mean latent space, because we're talking about the probability solution, and we need that scale as a standard deviation in this latent space. The latent space with the probability distribution side. So essentially, what you do here is you pass X to the intermediate layer at first, which you have them, and then the output of that you pass it to mean, like the FC mean, and FC standard deviation, potentially after applying deviation functions, of course. Exactly, that is the mapping process that I made here from this multi-dimensional feature map to the 1D feature space being a probability distribution. Is it that's enough? Yeah. Okay, nice. Thank you. Yeah.
It becomes temporary start.
Yeah.
Because
Exactly.
Like we have max of 10 minutes.
Oh, okay.
Yeah.
Then
So that's what we're.
yes.
Unless we want to stay for the whole night here, right? Yeah.
I think the office manager will kick us out after an hour or something. Huh? Okay, so I thought it was quite well what we did for part one. So let's do that again, basically. Exactly. So we're again in our full example notebook. Here we see the sections basically. Okay, we start with the setup, the same thing as last time. It's not very interesting. Then we start by defining the encoder, then a potentially symmetrical decoder. Then we put both the encoder and the decoder, which basically will handle our data. We put them into a variational autoencoder as like a combining model, and then we will train the VAE like the autoencoder, and maybe look at some examples or some generated samples. Exactly. So here this part in the setup part, the data loaders, we don't worry too much. We don't need to worry too much about it. This is just like PyTorch boilerplate code. I kept it in because of course there's not a PyTorch tutorial, but a Pyro tutorial. Exactly. So first we start with the encoder. Now, one important part about both the encoder and the decoder is that there is nothing probabilistic about them at this point. So we actually initialize them from the NN module, not as a Pyro. PyTorch layers. Now, this is one of the cases where there is not like a true solution, or like this is basically just an example. Like this, so right or wrong. I went with 2 convolutional layers, a batch normalization, and then 1 intermediate fully connected layer, and then a fully connected mean output layer, because we want to describe a probability space, not a deterministic latent space. So we need a mean basically and an average as parameters for our normal distribution that describes the latent space, and exactly, and we end up with 32 latent dimensions. Are there any particular questions about that? Because if not, this is mainly just PyTorch stuff. Then I would skip over that. You could also just use 2 fully connected layers here. Probably the results will then not be quite as good, but yeah, as I said, like there's no right or wrong here. As activation functions, I am using only soft plus, and we need to flatten our input at some point, so we also initialize a flatten layer here. The forward pass, I think, is relatively straightforward. We pass our X through the convolutional layers. We flatten it. I think exactly we do also batch normalization, which is not technically necessary for the training, but I noticed that it helps with the faster convergence, so I kept it in. Exactly, and then we output as at the end our Z, like describes our latent space, and then log, like the mean in our latent space, and the standard deviation in our latent space. The FC mean layer does not get an activation function applied to it because it is a number. It doesn't need to be in that sense activated or transformed in any way. For convergence and for inference, it is beneficial if we're predicting here the log variance instead of the variance directly. So we pass the output of FC STD to torsional exponential to actually do that, and then we return Z log and Z scale, which the decoder will use in the next step to sample from the latent space. This is just a way to look at the shapes in your model, which can be helpful. It is not necessary at this point. Exactly, and then we get to the decoder. We have one, like input layer again, fully connected input layer, one intermediate layer. Here we go from 32 input features and expand from there. Right, this is the compression in the encoder that we saw before, and the decompression now in the decoder. And since we have convolutional layers here in the encoder, we have transposed convolutional layers, so basically the inverse of the convolution here in the decoder. Exactly, and in the end, we basically just use another fully connected layer to bring the output into the correct shape that we need for our images. Again, we're using soft plus as the common activation function. We're using sigmoid, the sigmoid activation function as well on the output, since the output describes pixel intensity, which for the purpose of this model is defined between 0 and 1. We will see later also how to transform this back into the original range. And again, we're using flatten at some point to transform our 3D output into a 1D output. Exactly. Again, I think the forward method is quite straightforward. We just apply our layers in order together with the activation function and apply the sigmoid activation function to the output. And in the end, we reshape to 12828, which is the original shape of our inputs. -1 is the batch dimension. So we have batches of 128. So this is going to be this X is going to have size 128 in most cases. We have one color channel since we have grayscale images. So this basically, this channel or this axis describes the color intensity. So it's going to be for the purpose of image display, so to speak, is going to be a number between 0 and 255, while for the purpose of prediction, so to speak, with our sigmoid function is going to be a number between 0 and 1. So we need to expand this later on to fit to the original range. And then we have a width and a height of 28 pixel, so square images. So this is basically the PyTorch part of this notebook. Any questions so far? Maybe also for people who are not too familiar with PyTorch, but as I said, like in this case, there's no wrong way of doing this, basically. Because then I would move on to the actual VAE. Exactly. So this one, this one at the top level is also only like a non-probabilistic model. So we subclass here from the NN module, and we initialize our encoder that we previously defined and our decoder that we previously defined. Inside the initialization function, we also define here the latent dimension just for later usage. At this point, everything is completely probabilistic. Things are only getting registered with Pyro actually here in the model method, which is the callable basically that we need to to do the encoding. Exactly. Scrolling is a bit difficult. Exactly. So here in the model method, we actually start by registering our decoder as a Pyro module, so that all the parameters in our decoder are registered with Pyro. And then we essentially go directly into the plate. I think we could do this also outside of the plate. In this case, we just do it inside the plate. We define here something that acts as our prior for the latent dimension. So we define a Z log and a Z scale as Z log as zeros with one row for each row in the input, which in most cases will be 128, since we have a batch size of 128, and Z dimension 32, because we have 32 latent dimensions, columns for log, so of zeros for log, because we mean zero, it's just a standard normal distribution, and ones for the scale, ones of the same size for the scale, right? And then we actually need to sample from our latent dimension using these Z log and Z scale as the parameters for our latent dimension, for our sampling from the latent dimension. Important here is that we call this sample site something that is unique and ideally reusable, because we need to later on in the guide give this sample site, the corresponding sample site in the guide, the same name. We will see how it looks in a minute. Exactly, but we're going to sample from Z, and every sample from Z has one dimension because it's a 1D vector. So we set to event to 1 because we want to reserve one, the rightmost dimension for the event. Exactly, the sample of our let me scroll a bit to the right. Yeah, exactly. Yeah. So the sample from our latent dimension, we pass it through the decoder and get a log output. So the decoder, as you've seen above, only gives us one output. It doesn't give us two output like the encoder does. So we get here a mean basically of a sample from the latent space. This mean we are passing here to our distribution for the observations, which in this case we chose a continuous Bernoulli distribution because the pixel density that we are interested in within our image space is defined between 0 and 1, which also applies to continuous Bernoulli distribution. Exactly, the only parameter that we have here is our log output, and we need to sample exactly like the three rightmost dimensions from this output need to be reserved for the event, because in the end we're going to have 3 dimensions in the image, right? Because here we have a mean value for an image, right? You remember that the decoder had an output shape of 12828, so that's an image shape, and we are passing here the images as well, which also have a shape of 12828 per sample. So these are 3 dimensions. So each event is defined by 3 dimensions. So we need to define or reserve, so to speak, the 3 rightmost dimensions as events. Yeah, exactly. So that is now the model method. Now we need to define a guide. So the guide in this case is essentially responsible to find the latent space itself. So the model, like the above method, was the decoder essentially in our VAE. You saw we registered also the decoder network at the top. Yeah, exactly. Now we're going to get to the guide. It's a lot smaller. We basically just again register our encoder as a Pyro module, and then use the encoder to transform X, to map our X to some Z log and Z scale. So basically the same parameters that we the same parameter names that we already were looking at here. And we're going to use these two learned or fitted outputs as the parameters for another normal distribution that we give the same name as the other Pyro sample above. Because these two are now connected basically, and we again need to define an event dimension of 1, so the rightmost dimension is 1. Exactly. So that is pretty much all there is about the guide. At the bottom, we just have a bit of boilerplate code. I think I also left it in for the empty template. That's just how we could encode and then decode an image. I think that's pretty straightforward. Any questions so far before we go to the training part? So far, okay. Exactly. And exactly. So the training part is, I think, quite familiar to what we did before. Again, we have our SVI class. We use Adam as an optimizer. Learning rate, of course, we can play with that. This time we pass the callables, so the methods of our VAE as the model and the guide respectively. And we use the resulting SVI to train our model. I think most of this is quite clear. Here we have now batches as opposed to not having batches in the previous example. We calculate our loss at the end of each, like every 10 epochs out of 100. One thing to note maybe is here that more epochs will, in my experience, or I think in general experience, not lead to overfitting here. It just will stop training at some point, which you can also see here. So probably 60 epochs would have also been sufficient in this training process. But if we now look, exactly, we get like a minus 1,850 as like as a final elbow. Or as a final loss, if we now go down a little bit and look at the test loss, we see test loss is almost identical, just a little bit higher. But this indicates our model has trained well. I personally was not able to get a better loss than this. Of course, feel free to experiment a little bit with the models that we looked at above and maybe drop me a message if you were able to do that. But exactly, here we just look at the embeddings. Is very similar to what you already saw on the slide deck. I will not go into too much detail about this again, but further down we can now create some new images. It's also described how we do that. Essentially, we just need to sample like some kind of vector that we give to the model. If you remember about the model, the encoder part is quite insensitive to anything that you pass through it outside of training. So the output here will just have 28 samples with 32 latent dimensions and 32 columns. So it will be a 28 times 38 matrix. We make sure to reshape it appropriately for display. The leftmost dimension here is the batch dimension, and then we have a height and a width of 28 each. For display, we actually don't need the channel axis, so the pixel identity intensity is encoded in these two axes. And exactly. Then we can, through very nice, some of them less so. Some of them you can guess that they're a bit in between the different clusters. I'm not sure, did I actually run this before? I did. So let's see. That's probably a 3. That's probably also a 3. That's probably nothing. I could run this a bunch of times, and then we will see that some of these will be very nice, some of these will not be very nice. But this is pretty much it. I think we are just a little bit over time now. Are there any questions so far? Yes.
if I would like to feed the model, like with some more sophisticated images, should I just add some more convolutions to the encoder and like no, in the coder,
Like-
or should I work on the latents?
By more sophisticated images, you mean like not
Not
grayscale, big
mixed bar,
colors,
but like yeah, like
cats and dogs.
cats
something
and
like
next
that,
to
yeah.
hot dogs. So it's,
Yeah. So it depends. That's again something that I think we would find out through experimentation with the model itself. Actually, I think getting like more sophisticated features, more sophisticated images with cats and dogs, for example, with exactly with this kind of model. So with this relatively simple variation autoencoder, I think it will be difficult. If you would like to try, I would take a look at the encoder and decoder, maybe indeed add some more convolutions. But I think it's going to be tough. I think for more sophisticated features, we need to need a different kind of variation autoencoder. For example, a conditional variation autoencoder. They are a bit more complex, but they are, let's say, more likely able to deal with that kind of data. Okay. Yeah. Any other questions? Thank you. Not far. That's good. Because then, I mean, of course, if any other questions come up, drop me a message, let me know. But otherwise, you're welcome to help yourself to some snacks and drinks and refreshments. Right.
Thanks a lot. Thank you.
Thank you.
And so far we get the comments, very relevant examples. Thank you for the preparation of the material and slides. Yeah, that's what we got from those who watch us online.
My pleasure.
Thanks.
Thank you, everybody at home. I'm not sure. Can they still hear me?
Yes.
Yeah, okay.
Yes,
Thank you,
yes,
everybody.
yes. But in a couple of seconds. Yes.
Enjoy your evening.